and field at the surface of a conductor. Charge and field at the surface of a conductor. All right? A very important concept, so listen carefully. A conductor allows free charges to move within itself. Now, this is an aluminum rod, it's a conductor. If I have some free charges inside here, it will allow the free charges to move. Now tell me, what will make a free charge to move? Well, in order to make a free charge to move, you must have an electric field. Only an electric field can produce a force on a charge. So, if I have an electric field inside this conductor, then the free charges inside this conductor will move. Alright. If there is an electric field inside a charged conductor, it will make free charges inside it to move, causing an electric current to flow. Now, is this going to be true? If I place some excess charge on this aluminum rod, will there be electric current flowing in this? Well, I don't think so. Well, what does that mean? If there is no electric current, it means the charges are not flowing. And if the charges are not moving, it means there is no electric field inside the conductor. You see, that's a very simple conclusion. So, this causes redistribution of electric charges in such a way that there is no net electric field inside the conductor. So, if you charge a conducting material, then there will be redistribution of charges occurring in such a way that there is no net field inside a charged conductor. Now remember, in the previous case we talked about a charged sphere. That is not a conducting sphere. It is a non-conducting sphere. We talked about the electric field inside that material. But if it is a conducting sphere, there will be no electric field inside that sphere. The electric field inside a conductor will be zero. Why? Because if the electric field inside a conductor is not zero, then the free charges inside the conductor will be in a state of perpetual motion. You know that a conductor contains free electrons. And when these free electrons are in a state of perpetual motion, there will be a perpetual electric current in that conductor. Well, that would have been fine for us, but that doesn't happen. Therefore, our conclusion is there is no electric field inside a conductor. When this happens, all the free charges will reside on the surface. So, if you give free charges for a conductor, all those free charges will reside on the surface. We can use Gauss's law to show that when there is no net field inside a conductor, the net charge inside the conductor is also zero. You see, if there is no net field inside a conductor, that means there is no net charge. So, if you charge a conductor, if you supply electric charges to a conductor, where will all the free charges will be found? They will all be found on the surface of the conductor. No electric charges will be found inside the conductor. So we can conclude the following about a charged conductor. Very important conclusions. Now this is a charged conducting object. What are the conclusions about a charged conducting object? 1. All the charges on a charged conducting object will reside on its surface. Second, the electric field inside a charged conductor is zero. There will be no electric field inside a charged conductor. 3. The electric field at the surface of the conductor is at right angles to the surface everywhere, irrespective of the shape of the conductor. Now, what does that mean? If you have a conductor like this, that statement says the electric field at any point on the conducting surface will be at right angles. Now, what happens if the electric field is not at right angles? Now, suppose the electric field is like this, not right angles. If the electric field is like this, you know that a vector that is at an angle has a horizontal component and a vertical component. So, if the electric field is like this, there will be a component of the field along the surface. And if there is a component of the field along the surface, that electric field will make these electric charges to move. Again, it will create a current on the surface of the conductor. Since that doesn't happen, we know it doesn't happen. Now, since it doesn't happen, we can conclude that there will be no electric field along the surface of the conductor, which means all the electric field is at right angles everywhere on the surface of the conductor. The electric field at any point on the surface of the conductor will be at right angles, irrespective of the shape of the conductor. So you must be familiar with these properties of charged conductor. Let's do an example. An uncharged metal slab has square faces with 12 centimeter sides. It is placed in an external electric field that is perpendicular to its face. Now, you should know that if there is an electric field in this room, if I place an uncharged metal slab in the electric field, what will happen inside that metal slab? Remember, the electric field will make free charges to move. So inside the metal slab, the electrons will move opposite to the direction of the field. Remember, the direction of the electric field is the direction of motion of a positive charge. That means the electrons will move opposite to that. So if there is a field going like this, now is it from left to right for you? Yes. If there's an electric field that goes from left to right, the electrons in this metal will move from right to left. They will all get accumulated on this face, leaving the other face positively charged. So the net effect of placing this metal slab at right angles to an electric field is one phase of it will get negatively charged and the other phase will get positively charged. We call it the induced charge. You see, each phase will get induced electric charge. Alright, the total charge induced on one of the phases is 1.2 nanocoulomb. Now you understand what's the meaning of the induced charge. What is the magnitude of the electric field? What is the magnitude of the electric field in which that metal slab is placed? Okay, now here is the metal slab and this is the electric field. One phase of the metal slab gets induced negative charge and the other phase gets induced positive charge. The surface charge density on the metal slab, sigma, is Q over A. Is that right? If Q is the total induced charge, then the surface charge density will be Q over the area. What is the area of one side of the slab? It is of side 12 centimeter. Area is 0.12 multiplied by 0.12. So Q, the induced charge, we are given the induced charge. The total induced charge on one of the faces is 1.2 nanocoulomb. So that Q is 1.2 nanocoulomb. That is 1.2 times 10 to the negative 9 coulomb. And the area is 12 centimeter times 12 centimeter, 0.12 meters squared. That will be 8.33 times 10 to the negative 8 coulomb per meter squared. And that is the surface charge density. Now, the field outside a charged conductor is En equal to sigma over epsilon naught. Well, if you don't remember this, you need to remember this. The electric field outside a charged conductor is sigma over epsilon naught, and sigma we just calculated, epsilon naught we know. Therefore, that will be 9,416 Newton per coulomb is the intensity of that electric field.